What I would like for us to be able to do is to look at the original integral and within like a second or two, pretty much know which approach we want to take on it, or that has a really good shot at working. That's what I'm going to talk through in this video. All of my work is posted there for you to figure out the nuts and bolts parts of the problem, but getting that right approach down, that's going to be huge there to make sure we're always getting at least some sort of major partial credit on these problems, all right? So on this first one, it's not a UDU, but I see that a squared plus u squared pattern, so I'm going to use that trig substitution. This next one, I see that odd power with the trig. So that's when we're going to make that cosine squared, save the one, convert the other using Pythagorean identities, and just be careful with all your balancing there. On this one, I see like a normal thing and then times some weirder stuff. So that tells me I'm probably going to use integration by parts on that. I can actually use the shortcut on that because my u is equal to that x and my dv is the sine x cosine x. I can integrate that dv with the simple u du, and I can take that u part, I can take that derivative all the way down to 0. So I'm going to use integration by parts because I see the normal thing times the weirder thing, and I'm going to try to use that shortcut. That shortcut will work on that. Next one, notice that the numerator degree is higher than the denominator degree, so long division. Got to do long division first. Now, after you do long division, you're going to be able to factor that denominator, then you can use partial fractions. But if you don't do the long division first, you're going to be missing terms in your final answer there. But since you can factor that denominator, eventually it's going to be partial fractions. Same thing as the next one, I can factor that denominator, so I'm going to use partial fractions. Number 6, we got a normal thing times some weirder stuff. That's going to be integration by parts. I can let the u be that x squared. I can take that derivative down to 0. I can integrate that sine of 2x if that's my dv. So I'm allowed to use my shortcut, my tabular method on that one. Whenever we have a secant to the fourth, that's when I want us to make that secant squared, keep one of the secant squares, change the other one using the Pythagorean identities, and then you'll distribute, and then you'll have a couple of integrals that you can integrate. Either it'd be like a reverse derivative integral with your balancing, or a UDU, or a couple UDUs in there. Next one, whenever you see the ln's in your problem, your u has to equal the ln part of the problem. Whenever you see an arc function in your problem, your u must equal the arc function in the problem there. Now, it's either going to be a UDU, you got to take that du anyhow, or it's going to be integration by parts. This one, if you let the u equal the ln of sine, when you do the derivative of that, is not quite matching up with that cosine of x there, all right? So this is going to be an integration by parts. If you have an ln in the problem, let the u be the ln part, and if it doesn't work out the UDU, it's going to be integration by parts. Next one, you could factor this denominator by grouping. So I can use partial fractions. The number 10 there, you see that a squared minus u squared pattern. So that's going to be trig substitution again. Number 11 here, if you let the u equal the weird angle and you do your du, take that derivative, it's going to work out with a simple u du. This number 12 here, you're going to need to multiply that out. Write that down twice, like sine plus cosine times another sine plus cosine, multiply that all out. And then there's a longer way to do it, but after you multiply it all out, if you recognize that you have a sine squared plus cosine squared, you could make that a 1. So then you'll get a 1 plus something, and then you'll be able to integrate that a lot easier there. Number 13, you have another ln in that problem, but this one's going to work out with a UDU. You got to let the u be the ln part, but when you do your du, you're going to get that 1 over x dx to match up. So that's going to be a UDU. This next one here is going to be one of those hidden UDU problems. If you let u equal secant, the derivative secant is a secant tangent. So you not only get that tangent to match up, but you also get a bonus secant to match up. So then you'll be integrating that u to the third there. So we had a little bit of that in that trigonometric integral section there. Number 15, I see on the top there, I see a u squared minus a squared pattern. So that's going to be my trig substitution. Now, remember when you're doing trig substitution, you got to make sure you know all 3 of those main properties from our notes there, like which one to start that with, you know, your tangent pattern, your sine pattern, or your secant pattern right there. So make sure we got those down. And then 16, you see this odd power, right? So you got that odd power in there. That's when you're going to make that cosine squared, save the one, convert the other. Only use those even identities if you only have an even integral. I think when you do number 10, when you work this out, you'll be like eventually in the middle of that thing, you'll get like the integral of sine squared or the integral of cosine squared, and you need to use the even identity since you only have the even powers with the sines and the cosines in there. Number 17, if you let your u equal that whole numerator, your du will give you that denominator there, so it'll match up. You gotta be careful with the balancing, but that can work out with the simple u du right there. Number 18 is I'll probably bring that up and make that x e to the negative x. And I have a normal thing times a weirder thing. I can just use my tabular method. I can use my integration by parts shortcut on that. 19, when we see this trinomial stuff and it's not working out with some UDUs there, whether there's a square root there or not, that looks like we're going to need to do completing the square. And then after you do completing the square, it's either going to turn into one of your arc functions right away from our blue sheet, or it's going to turn into a trig substitution problem right there. But that one, I think it should turn into some arc function right away. All right, this one's just a UDU. If you let your u equal a tangent, the derivative of tangent is secant squared. So that's a UDU. Look at you right in the face. This next one, you have a normal thing times a weirder thing. Got to do integration by parts there. Your u must equal the arc function, and then you're not going to be able to use the shortcut on that one. So you got to use that integration by parts formula, uv minus the integral of v du. Number 22, if you have a single e in the problem, try to let the u equal that power first. Your du is going to give you this negative 1 over x squared. So you're going to get that denominator to match up. That's going to be a simple u du. And then when you have the odd powers there, basically you just got to pick one. Try to be persistent with that. It's been my experience. If I got tangent cube, secant cube, or like on this one, cotangent cube, cosecant cube, if I pick the tangent one or the cotangent one and play around with that guy, that's the one that's going to work, where I'm going to get something in the middle of that, and I'm going to have something that I can integrate. So if you play around with that and you make that, do your normal stuff, like choose the odd power, but you're going to choose the cotangent odd power, make that cotangent squared, and then use your save one, convert the other using Pythagorean identities in the middle of that, you're going to eventually get one of those hidden UDU problems, and it'll work out with the UDU in the middle of that. All right, so try my work. Use that work responsibly to help yourself there, practice these a bunch, and then make sure you're studying the beginnings of these problems to make sure that you're approaching all of them the right way. Also, hit the other review, because the other review reviews your L'Hopital's rule and your improper integrals and all of that weird limit stuff there. And this focuses on all of our integrals.